Hello and welcome to Lecture 5 on the nervous system. All right, so we're going to talk about properties of nerves, neurons, the brain, the spinal cord, the major parts and pieces found here. Let's begin with a quick conversation on how your nervous system really works, okay? The idea here is as follows. For anything that you do, it can be broken down into some sort of sensory input, followed by a processing referred to as integration. This oftentimes happens at the brain. It can happen other places, but oftentimes happens at the brain, followed by some sort of motor output. So I could say hello to you. That would be a sensory input. You would integrate that, think, oh, I need to respond, and you would say hi back. That is a sensory input, integration, motor output. Or alternatively, you could be driving down the interstate and come around a corner and see, corners being relative on the interstate, see our policeman friend here scanning cars for their speed. You would integrate that and realize you don't want to have a speeding ticket, and regardless of the speed you're going, you're going to take your foot off the gas. That is a sensory input, seeing something. Integration, figuring out your response, and then a motor output of doing something. And it can be deeper than this. This could be picking up variations in blood chemistry and driving you to make physiological changes internally that you aren't even aware of to deal with your changes in bodily chemistry. All right, it could be internal and you're never aware of it, or it could be external, as my examples here are showing. Like our buddy here trying to pose for one of the best profile pictures ever, and sitting next to one of nature's finest killing machines. It's probably got him a little bit on edge. So the big cat gives a little bit of a head nudge, which is enough of a sensory input that this guy can then integrate that he needs to escape quickly, and his motor output is to dive off the balcony. All right, so all of it, it's all about sensory inputs, some sort of integration, and then a following motor output, a response, as it were. Now, the nervous system has two cell types. There are neurons and what are called neuroglial cells. Neurons are the main cells that send messages from place to place. Like when you think about your nervous system as being capable of transmitting messages, it's the neurons that are transmitting messages. The neuroglial cells are different. Neuroglial cells are assistants. They are helpers. They facilitate the neurons in their general activities. They clean up after them if they are wasteful. They provide nutrition in the event that is necessary. Neuroglial cells do much to assist the nervous system, whereas the neurons actually conduct the physical messages. Now, major properties of neurons that are worthy of our consideration are as follows. Neurons are excitable. That means that you can stimulate a neuron and it will be stimulated. There are cells in your body that don't work that way, all right? But I can expose a neuron to a given chemical and it will respond to that given chemical. They are excitable. They are capable of being augmented by their environment. 2, they are conductive. That is, that if I stimulate one side of a nerve, that stimulus will travel to the opposing side. If I stimulate the dendrites of a neuron, which you'll hear about shortly, you can expect that stimulus to flow through to the axon of that neuron. So they are conductive. They are capable of sending messages over long distances. I can think flex big toe, and my big toe flexes because I'm capable of sending messages over long durations using my neurons. They are conductive. And last but not least, neurons are secretory. The way that neurons are capable of communicating with other cells, of sending messages to other cells, is because those neurons are capable of secreting chemicals referred to as neurotransmitters. When I think flex bicep and my bicep flexes, it's because I'm releasing neurotransmitters for a neuron, an axon terminal as it were, which you should be aware of at this stage, releasing neurotransmitters which bond to that muscle and stimulate it to become contracted. Okay, so our neurons are indeed secretory. They release chemicals we refer to as being neurotransmitters. And that takes us to here. Now, we have spoke previously about, man, I'm losing it here, folks. I've been teaching all week and my voice is just dying. We had talked previously about how there are sensory neurons, interneurons, and motor neurons. Let's add some terminology to that. So we'll compact it a little bit. So there are sensory neurons which send afferent messages. Okay, sensory neurons send afferent messages to some sort of control center, interneurons, and those interneurons will then send out efferent motor messages to some sort of cell to do a job. So sensory neurons, interneurons, motor neurons. Sensory, interneurons, motor neurons. Now, let me ask you a question. Which of these do we predict would be more numerous? Sensory neurons, motor neurons, or interneurons? And the answer is very simple here. And that is that interneurons are far more numerous than the rest. Think about this. I can see the wall. I can make decisions to move. Or I can physically move. But deciding what to do is complicated. All right? Someone can come up and say something to me, and I can hear them. I can put my hand down. But understanding the appropriate response to what I'm being told, that's complicated. So there are far more interneurons involved in processing information, physically making decisions, than there are sensory neurons and motor neurons. In fact, vastly more. More than 90% of your neurons are going to be interneurons, whereas those that are sensory or motor are far more limited by comparison, and far more simplistic in their appearance. They are very simple compared to the big, highly branching interneurons. Okay, this slide is incredibly important for us. We will be using this graphic for the duration of the rest of the semester to go through and talk about general functions of your bodily systems. Now, let's talk about it. So what we have is the central nervous system, also called the CNS. This is your brain and spinal cord. And then below this is going to be the peripheral nervous system, which are your major sensory and motor neurons. If you look at our image here, the brain and spinal cord comprise the central nervous system, whereas everything else would comprise the peripheral nervous system, or PNS. All right? Now, we can break this down a little bit. So the peripheral nervous system is indeed sensory versus motor, but we can go down a little further. We call these the somatic sensory division and the visceral sensory division, the somatic motor division and the visceral motor division. Somatic means of the body, okay, of the body. So somatic sensory, I feel the table. I see the camera. It's cold in here, and I can feel it. I'm consciously aware of it. Things which we are consciously aware of tend to be somatic sensory signals, all right? Conscious awareness. Visceral sensory, this tends to be like sensing your blood chemistry, which you're not directly aware of. Sensing your oxygen carrying capacity and responding accordingly. Internal sensations, sensing that food is moving out of the stomach into the small intestine, and then having the brain respond to bring about changes to the small intestines for digestion. You're not aware of it. Visceral sensory information you tend not to be directly aware of, or if you are aware of it, it's vague. Like you can potentially feel if your heart's beating fast, you know what I mean? But it's vague, it's a vague sensation. Now, by comparison, somatic motor versus visceral motor, again, somatic means of the body. Somatic motor is anything that you are consciously aware of doing that is a motor output. I can stand up, I can walk around, I can speak to you, I can move my eyes. Pretty much everything dictated by skeletal muscle, because skeletal muscle is voluntary. All right, so the somatic motor division pretty much controls skeletal muscle. The visceral motor division, by comparison, controls every other motor output from the brain, and it can be endless varieties here. Regulating your pupil diameter, regulating how constricted or dilated your blood vessels are, regulating how quickly you grow. Like all of this would be visceral motor outputs, all right? These are all going to be visceral motor outputs, and it's so complex. There is so much going on in the visceral motor world that we apply a special term set to this. We call the visceral motor division your autonomic nervous system. And the autonomic nervous system is comprised of two parts. These are the parasympathetic division, the sympathetic division and the parasympathetic division. And the idea is that the sympathetic division rouses body parts for activity. So thinking about like making your heart beat faster, whereas the parasympathetic division cools the body down and relaxes you. So these work in opposition to each other in a lot of cases. Like you can imagine that the sympathetic division dilates the pupils, whereas the parasympathetic division constricts the pupils. Okay, they kind of work against one another to keep your body in homeostatic balance, right? You'll oftentimes hear the sympathetic division referred to as giving a fight or flight response, and the parasympathetic division giving rise to what we call a resting and digesting response. So, good enough. Let's just leave it there for time being. All right, let's go here. Here are some general neuron structures and some ideas on conductive properties. Now, a neuron is structured as follows. There are dendrites, a cell body, and an axon. The concept is that dendrites receive information, the cell body processes information, and the axon sends information. Okay? Here we have dendrites. You could expose those dendrites to a neurotransmitter. That neurotransmitter would stimulate the dendrites, which would in turn stimulate the nerve cell body where the nucleus is housed. That will be important later, where the nucleus is housed in the nerve cell body. That could then move towards the axon and stimulate the axon to send a message all throughout the body. All right, send it somewhere else. The axon tends to be quite long, so you'll have axons that reach from your spinal cord way on down to the tips of your toes. Okay, so the axon conveys messages away from the nerve cell body. All right, that's good enough. We've already sort of talked about neuroglia, but we're going to talk a little bit more about them. What you see here is your good old-fashioned neuron. There's a big old honking neuron right there. There it is, real pretty, looks kind of like that. There's a neuron. These little dark spots all around it, all right, all these little dots, those are all going to be neuroglial cells. And neuroglial cells, again, are the helpers typically. They do things that assist the neuron in its general function. And one of the most important things that neuroglial cells do, one of the most important neuroglial cells, of which there are many types, are Schwann cells. Schwann cells are a type of neuroglia. Now, what makes Schwann cells important is their ability to make a lipid substance called myelin. Myelin, right there, called myelin. And what myelin does is it works as an insulator for your neurons, for your axons specifically. You see here on our axon it says myelin sheath. That myelin sheath would be made by Schwann cells. And when Schwann cells are there, when the myelin sheath is present, that nerve is capable of sending messages much faster. It will speed up conduction times. So you can conduct a message faster on a myelinated neuron than you can with a neuron that is not myelinated. All right? When myelin is present, the conduction speed is higher. It's faster. You can send a message quicker. So you can imagine that really short little neurons like those between your nasal epithelium and your brain that are only like yay long, they're not going to be myelinated because that's going to be pretty quick transmission speed regardless. But the neurons that innervate the muscles in your legs, transmitting all the way from your brain to your legs to kind of keep you upright so you don't fall down, those have to convey their messages at a faster rate. So they're going to bear myelin. They're going to have Schwann cells, and they're going to bear myelin. Now, the myelin sheath also serves another incredibly important role that I think is worthy of our consideration. You probably realize that in your central nervous system, your brain and spinal cord, if you damage nerves, they don't heal back. So why people have spinal injuries and they no longer are capable of moving. But alternatively, if you damage a nerve in your arm or in a leg, somewhere out in the peripheral nervous system, it's possible that you could then heal that nerve and get back full function. You can completely cut the nerve off and it will grow back, or it can grow back. And the reason it can grow back is because of Schwann cells. You see, when you cut a nerve, everything downstream on the axon from the damage, it all dies. You're basically cutting off a piece of the cell, so it all dies downstream. And what will have to happen is the nerve will have to regrow the axon. When Schwann cells were present, the Schwann cells live on. The myelin sheath lives on. And it will form a tube called a regeneration tube. I'm sure I've got this on. Yeah, forms regeneration tube that will guide the axon right on back to where it needs to be. All right, and that's good enough for me. I'm going to talk about gray matter and white matter here in a little while. The idea is that in your brain and spinal cord you have gray matter and you have white matter, and these are dependent upon the presence or absence of myelin. So gray matter and white matter would be myelinated axons, whereas gray matter will be nerve cell bodies. They appear gray, they appear darker in color because they contain the, what do you call it? Nuclei, the nuclei of the cells, nuclei. All right, good enough. And here, what we need to talk about now is why myelin speeds up nervous transmissions. Okay, myelin speeds up nerve transmissions, that is a fact. How does myelin speed up a nervous transmission? And the answer is that when myelin is present, you end up with what's called saltatory conduction. When myelin is not present, you end up with what's called continuous conduction. Continuous conduction is very simplistic. Do I have anything I can use here? Let's pretend. If we have a big, long nerve, okay, if I stimulate this side, that stimulus is going to flow down the length of the nerve until it reaches the opposing side. That is continuous conduction. It's continuous with no myelin in place because it starts on one side and transitions all the way down the length of that nerve to the opposing side. It is carried down the entire length of the nerve. That is continuous conduction. When myelin is present, however, you end up with what's called saltatory conduction. Look at this image. Can you see how you've got a Schwann cell, a Schwann cell, a Schwann cell, a Schwann cell, a Schwann cell? When you have myelin like this, okay, when you have a myelin sheath, instead of stimulating one part of the axon and the stimulus flowing down the length of it like this, you end up with saltatory conduction. Saltatory conduction indicates that a nerve's transmission will, golly man, this thing's driving me crazy, will transmit down to the myelin sheath and then leap it to the next piece of the neuron, and leap it to the next piece of the neuron, and leap it to the next piece of the neuron, and leap to the next, and leap. Saltation means to leap or to jump. So when myelin is present, in essence, the nerve transmission skips the areas where the myelin is, and it travels much faster by comparison. And that's what I'm trying to show you here. What we have is a nerve transmission running down the length of an unmyelinated neuron versus when myelin is present and the nerve transmission leaps from node to node to node down the length of that axon, taking much less time. When myelin is present, you get saltatory conduction, and that conduction pattern is much, much faster by comparison. All right, let's talk a little bit about a synapse. So a synapse is an area where an axon connects to a dendrite for our purposes. Okay, imagine this situation here where you got an axon coming down and connecting to a nerve of some fashion. Okay, if you look, these are axon terminals. They're coming down and they're not touching, but they're sitting very, very close to the dendrites, generally speaking, of an adjacent nerve. This would be considered a presynaptic neuron, a synapse, and a postsynaptic neuron. The key point here that you need to know is there's a gap between them. There's an open space. Remember the synaptic cleft and muscle fibers? Same concept. There's an open space here so that when an axon sends a message, which hereafter we will call an action potential. An action potential is a message traveling down an axon. When I think flex bicep, I send an action potential to my bicep and it flexes. Okay, an action potential. When a presynaptic neuron sends an action potential down the length of its axon and it arrives at the axon terminal, it can go no further. So how do I stimulate a postsynaptic neuron? The axon terminal releases synaptic vesicles of a neurotransmitter that can then cross the synaptic cleft and bind to a postsynaptic neuron. The idea is it's an electrical signal followed by a chemical signal which stimulates a new electrical signal. Neurotransmitters, that is how a neuron communicates with an adjacent neuron. It's all about these neurotransmitters. It's incredibly important. Yeah. I'm pretty happy with that. I think that'll do. Let's go here. I'm not going to go into detail on this. I think I've already explained that an action potential is basically a message that travels down the length of an axon. What I will say is that action potentials and the way that they transmit these messages deals with ions and their exchange. So you can exchange ions in an axon, and you'll see that area of the axon that is stimulated sort of depolarize and repolarize. It shows like a waveform like this. That's what I was showing you over here when we talked about continuous conduction. You can see the wave moving down. Imagine I had a rope and I put a loop in it, I give it a wave and the wave shoots down the length of the rope. Action potentials can easily be visualized because we can see their electrical signals. Okay, we can see a spike into positivity, and then the axon's internal environment will return back to negativity. Action potentials are how nerves send messages. And that takes us on to the central nervous system, folks. So let's go through and talk about it. It wasn't always clear to us what the brain does. In fact, some very intelligent people had no earthly idea how it functioned. Not terribly long ago, Aristotle was under the impression that the brain was simply a radiator for the rest of the body, because you feel your head, it's always hot, right? Incorrect. Hippocrates was closer. If you're not aware of Hippocrates, he's the father of modern medicine. If you become a doctor, you'll do a Hippocratic oath, okay? Do no harm. Hippocrates says the following: "From the brain only arises our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears," which is a little more accurate. The idea here is that everything we think about and everything we do is governed by the brain, and he's correct. The cessation of general brain activity, we can measure this electrically, is how we clinically define death. And if we look at the brain, you'll find that our brain has evolved to be quite different from most other animals in the world. Our brains are a little more complicated than most other animals, especially in the areas that control our hands, the areas that control our eyes, because our eyesight is fantastic compared to most other animals. For what we do, I suppose. Other animals can see in the dark. We can't. We have wonderful daylight vision, but it's good for us. It works for us. And the areas for memory. So our capacity for memory is pretty elevated compared to a lot of other animals. All right, let's go here. So the central nervous system is indeed the brain and spinal cord. All right, is indeed the brain and spinal cord. And these are going to be protected by bone. All right, your skull and your spinal cord certainly protect the soft parts of your nervous system. That is a fact. Your brain and spinal cord are protected by these membrane systems called the meninges. The meninges is a three-part membrane system that sort of helps the brain stay suspended in place, protects the brain. And then last but not least is a fluid called cerebrospinal fluid. It helps to kind of float the brain and forms a friction barrier, and helps to carry around nutrients and waste particles to keep the brain's environment cleansed. Okay? So these three aspects, which we'll talk about later on, are very important for general neural function. You got to have them. And let's see, what else do I want to say? Oh, we need to talk about gray matter and white matter. So gray matter is going to be the area where nerve cell processing occurs. This is where the nerves cell bodies are going to be found, called somas, the cell bodies, where the nuclei are located. That's gray matter. And then white matter will be myelinated axons, right? Myelinated axons. And if you look at this, here's the spinal cord. What you can see is gray matter in the middle. This is going to be dark because it contains those nerve cell bodies, which contain the nuclei. And then you've got these myelinated axons branching eternally out from this. So all of these, you can see how stringy this appears. It appears stringy because these are going to be axons leaving out from the gray matter here. Now, if you want to think about how big around your nerve cord actually is, it's like the size of the end of your pinky finger. Okay? It's very small. Smaller than that, really. A good bit smaller than that. A little bit bigger than like a number 2 pencil is the size of your nerve cord. But if you look at it, you can see the nerve cord in a real person here. These branches that are coming off of it, these are all going to be going out to the body so that you can convey messages away or bring messages back in to that nerve cord. The main concept of the nerve cord is it provides communication to and from the brain. So to and from the brain to the body, or from the body. All right, that'll work. And I'll say the following too, because your spinal cord contains gray matter, that means it's capable of processing information. And what your spinal cord does in terms of processing information oftentimes revolves around reflex arcs. So if I grab a hot pan, I immediately pull my hand away from it. I don't think about it, I just do, because that information that I'm going to burn myself goes to my spinal cord, and the spinal cord bounces it back immediately, instantaneously, and says, pull your hand off so you don't hurt yourself. And then I can think about what just happened, but I didn't even contemplate pulling my hand away. It just happens because the nerve cord contains gray matter and it runs reflex arcs. Think about like stepping on something sharp and you pull your foot up immediately. Same concept. All right, same concept. All right, so brain and spinal cord, that's gray matter and white matter. Gray matter, again, is the seat of cell bodies and their neurons, of the neurons, I should say. It will have a darker coloration, and you can see in the cerebral cortex out here, all of this is gray matter. Okay, all the dark area, that's all gray matter. You can see how wrinkly the brain is. The reason that the brain is wrinkly is to increase its surface area, thus giving you more area for gray matter, which is where we process information. The white matter, by comparison, is going to be these myelinated axons going to and from the gray matter. You may have heard some genius say that you only use like 12% of your brain or something ridiculous like that. That's absolute nonsense. You use your whole brain. It's just the actual processing centers don't make up a huge amount of the volume because they are confined to certain areas. Okay, that would be the gray matter. So you have gray matter around the outside, and you have some gray matter in what are called basal nuclei deep inside the brain. Okay, so these are all going to be processing centers, whereas the white matter is conveying information to and from the gray matter. This is going to be myelinated axons. Myelinated axons. Now, there are four major parts to the brain. These are the cerebrum, the diencephalon, the cerebellum, and the brainstem. The cerebrum is the big, outer wrinkly part here. The diencephalon is shown here in blue. Thalamus and hypothalamus being key amongst these. The brainstem is going to be the lower brain centers, pons, medulla oblongata, all that fun stuff down through here. And then the hindbrain is your cerebellum, which is this structure back here. Your cerebellum, you need to think about this as being a completely independent brain unit. You have your cerebrum, which is a brain by itself, and you have the cerebellum, which is a separate brain all on its lonesome. Okay, it will do different things, it has different jobs, it runs different aspects of the body compared to the cerebrum. Okay, they are two separate units, they are not directly connected. In fact, you can take a brain and grab the cerebellum and pull it down. They are completely separate. All right, good enough. Let's go here. All right, let's talk about the cerebrum. Now, your cerebrum is big and conspicuous. It's made of these high spots called gyruses and low spots called sulci or sulcuses. So gyruses and sulcuses. Your cerebrum is indeed the seat of major sensory perception, memory, thought, judgment, you name it. A lot happens here. In particular, the storage of long-term memory and general inputs of sensory information. A point to be made about the cerebrum is that it will decide what to do, not necessarily how to do it. Like you might decide you want to get up and walk across the room, but other parts of the brain will physically raise you up, move your feet from place to place, and increase your blood pressure so you don't pass out. All right? So the cerebrum is like the general, and the foot soldiers are elsewhere. Okay, the ones that actually do the job. Now, your cerebrum is broken down into a number of lobes. To keep this simple, we're going to address 4 of these. I will address the frontal lobe, parietal lobe, occipital lobe, and temporal. Frontal, parietal, occipital, and temporal. Okay? The frontal lobe is probably the most important amongst these. Your general disposition, that's your frontal lobe. The actions you decide to do consciously, it's all frontal lobe. Your responses to people when they talk to you, it's all frontal lobe. Like your frontal lobe determines who you are. Your personality is your frontal lobe. The parietal lobe, as seen here, is general sensory. It runs things like taste, for instance, and all of our skin sensation. Like I can feel this table and tell you it's cool. I can, put pressure against it and I can feel the pain and pressure from my hand. That's all going to come in via the parietal lobe. The occipital lobe, located on the back, which is kind of interesting. The occipital lobe in the back brings information in from the eyes and helps you to interpret visual knowledge. Okay, your occipital lobe plays a role in vision processing. And then last but not least, we have this temporal lobe. The temporal lobe is going to be involved in generally hearing and smell. Okay, hearing is the most important bit here. You got to imagine your ear is right here, so it's going to be connected right at the temporal lobe. and it's going to help you understand the things that are being said. Okay, your temporal lobe is important to hearing, and again, plays a role in smell. All right, let's go here. All right, on to the other parts of the brain. What we have here is the diencephalon and the cerebellum. So the diencephalon is going to be made up of the thalamus, kind of seen here. The thalamus makes up these two kind of ovoid masses on either side of the brain. So one would be in and one would be out. They look kind of like this. So they come up out of the brain stem, as it were. They come up out of the brain stem, as it were, into the two hemispheres of the cerebrum. The idea behind the thalamus, what was that? Was I talking? The idea behind the thalamus is that the thalamus forms a gateway from the cerebral hemispheres down into the brainstem. So the body sends information up, it goes through the thalamus out to wherever it needs to be in the cerebral hemispheres. And when the cerebral hemispheres have an integrated response, they send information down to the thalamus, which then sends it down through the spinal cord to wherever it needs to go. So the thalamus is very involved in conveying messages to and from the cerebral cortex. Yeah, that's good enough for me. That's what I want you to know. This is a little bit off from what I really would prefer that you guys in human biology know. I want you to grasp that it's a gateway to and from the cerebral hemispheres. All right, the hypothalamus, by comparison, is this little area here. It's kind of right above the pituitary gland and runs part of the pituitary gland, for that matter. Your hypothalamus is just so important. Please be friends with the hypothalamus. It really matters. The hypothalamus is your main homeostatic control center. Your hypothalamus is the autonomic control center. So all visceral motor outputs, they come from the hypothalamus at the end of the day. Things like your sensations of hunger, thirst, your capacity for a 24-hour circadian rhythm, that's going to be your sleep cycle, your body temperature regulation, so vasoconstriction, vasodilation, your general water balance and osmotic control of the kidneys. It's all going to be run via the hypothalamus. It is very important for this. So your hypothalamus, it matters, okay? It has a lot of functions and they are very important. You need to be friends with the hypothalamus. And then last but not least, here at the bottom is the pineal gland. The pineal gland is involved in secreting melatonin, which is involved in sleep. And I know you're going to be like, wait, didn't you just say that the hypothalamus controls sleep? Yes, it does. The hypothalamus controls the function of the pineal gland. All right? So there are bits and pieces of the diencephalon. Also in and amongst this, we have the cerebellum back here. So on the back of the brain, this hind brain, that is the cerebellum. And the cerebellum is indeed a little independent brain unit all by its lonesome. Your cerebellum is like your physical autopilot. If you decide to get up and walk somewhere and you realize when you get there you don't even remember the process, that's because your cerebellum took you. When I think stand up and walk across the room, that's my cerebrum deciding to do it. But that's my cerebrum deciding to get up and walk across the room. But my cerebellum decides where my feet go and how my body is to be oriented to keep me from falling down. All right? Your cerebrum is tightly tied into your equilibrium senses, your visual senses, and what's called proprioception, your stretch receptors in all of your joints and your feet and all that fun stuff. Your cerebellum guides your motion on a daily basis, puts you where you need to be, coordinates your functions, helps you go upstairs. That is all cerebellar in activity. It is a little independent brain all by itself. That's why you can be doing an activity mindlessly and be thinking completely about other things. That's because your cerebellum is doing it by itself, all right? Let's see, what else do I want to say? Your cerebellum also plays a very important role in what you might call motor memory. Is that right? Motor memory? Is that appropriate English? Muscle memory. There we go. Muscle memory. So you can, at this moment, lean over and tie your shoe and not even think about it. While you're doing other things, you can be watching TV or reading a book and tie your shoe, and it just happens miraculously. That's because your cerebellum ties your shoes for you. All right? Think about hitting a golf ball or swinging a bat, trying to put a bat on a ball. You're sitting there, and you're waiting on the ball, and when the ball's getting close, you begin the swinging process, but you don't think about it. That's a really complicated movement. You don't think about it at all because your cerebrum decides when to swing and your cerebellum coordinates all the motor activity necessary for that swing. Okay? Your cerebellum does the action necessary to get these little tasks accomplished. All right, I think that'll work. Let's see. Yeah. All right, that'll do. That'll do. Let's go here. The brainstem. So midbrain, pons, medulla oblongata. These are the bits I'm concerned with. I don't really want to talk a whole lot about these. They're just not as important from my perspective as what we've been talking about previously. They sort of just convey information to and from, and they can have some minor influences on the body. Like your pons, for example, regulates the rate at which you breathe, what that really means is that the hypothalamus controls this, but it allows the pons to take over the general function of it, all right? Your medulla oblongata controls your heartbeat and blood pressure. That's really controlled by the hypothalamus, but the medulla oblongata sort of regulates it from there and keeps the hypothalamus abreast of the situation. It's a little complicated. For my purposes, I want you to think about the hypothalamus as running the show. These lower brain centers are mainly concerned with carrying information to and from the brain with some control over lower body features. Okay, some control. I'll give you just one terrible example. We think that a pons malfunction might be what causes sudden infant death, SIDS, sudden infant death syndrome. We think it may be a pons related issue. So the pons stops sending breathing messages so the kid asphyxiates, which is awful in every way, but you know, sometimes health is bad. All right, here we go. Or you get my point. All right, moving on. Meninges and cerebrospinal fluid. So your meninges is a three-part system. They're composed of the dura mater, the arachnoid mater, and the pia mater. And the way I want you to think about this is as follows. These are membranes that surround and separate out the parts of the brain. They are membranes. The dura mater is basically attached to the skull, right? Dura mater attached to the skull, and the dura mater is like this super thick fibrous membrane, man. Like if you had it in your hands, you couldn't tear it in two pieces. Like it's very thick and strong. It's like a big old ligament, basically. It's like a huge ligament that's attached to the skull. The arachnoid mater is here in between the dura mater and what's called the pia mater. The pia mater is on the brain like skin on a grape. The dura mater is against the skull, and the arachnoid mater is between the two. And that's important because the arachnoid mater is made out of little elastin fibers. So as the brain is moving around inside your skull, messages. Moving on. So as the brain is bouncing around inside the skull, the pia mater sort of gives it some resilience. The pia mater acts like a shock absorption system so that as the brain moves around, it's not actually going to touch the skull and become damaged, okay, which is very important. So these meninges are very important for this as a concept. Also, they will bring arterial networks, blood vessels into the brain to help the brain be nourished. Now, cerebrospinal fluid, this is a fluid that bathes the whole outside of the brain. It's going to fill the arachnoid space where the arachnoid mater is. And cerebrospinal fluid fills the interior chambers of the brain. You may not realize this, but your brain is quite hollow, all right? There are large open areas within the brain, and they are full of cerebrospinal fluid made by special structures called choroid plexus. Choroid plexus makes cerebrospinal fluid, and that's located inside of these chambers called ventricles inside of the brain. Now, what does cerebrospinal fluid do? It makes the brain neutrally buoyant. It floats basically inside the cranial cavity, so there's no weight of the brain pushing down on the skull, so the brain can't touch the skull in that fashion, so it keeps it from becoming damaged. And also it protects the brain from motion. So you have been in a swimming pool before and you've tried to twist or walk quickly or anything along those lines. When there's a fluid medium it takes a lot to move through it. So by having a fluid surrounding the brain, if I move forward and it stops suddenly, if the brain tries to move forward, it has to push fluid all around itself to do so. And basically, the cerebrospinal fluid then acts like another set of shock absorbers that prevent the brain from touching the skull, which we do not want. We don't want the brain to touch the skull, because if the brain touches the skull, it will damage it, folks. That is a concussion. Okay? Concussions take place when the brain touches the skull. Think of it like a little brain bruise in the grand scheme of things. So cerebrospinal fluid helps to prevent that. And cerebrospinal fluid also serves a chemical stability role, sort of bathing the brain, removing wastes, providing a medium through which hormones can travel, providing nutrients in some fashion for the brain, oxygen, you name it. So there will be things in the cerebrospinal fluid that the brain needs, and thus cerebrospinal fluid provides chemical stability. Let's go here. All right, I want to talk a little bit about a structure called the blood-brain barrier. Now, I'm not going to go into a huge amount of detail on this. I think I can probably just explain it to you, and you'll be happy. Your brain has a barrier system. You see, your blood is a potential source of all sorts of toxins. If you're septic, your blood could bear bacteria. Your blood has constantly changing chemistry, oxygen levels, carbon dioxide levels, acidity, basicity. Your blood, man, it's always changing. And you don't want the brain to be exposed to this. You want the brain's environment to be uniform, always uniform. So what we have to do is we have to find a way to be able to get what we need out of the blood into the brain, but keep the crazy nature of the blood from affecting the brain's chemistry. And we do so using what's called the blood-brain barrier. Okay, the blood-brain barrier. Blood-brain barrier system. What this does is it strictly regulates what can come in and what goes out. Let me say that again. Your blood-brain barrier strictly regulates what can get into the brain. Now, some things get in quite readily, and I probably have this on here somewhere. Certain lipid-soluble substances, oxygen and carbon dioxide have to diffuse readily. Water can diffuse readily throughout this blood-brain barrier, so that it can get through with great ease. Whereas other substances cannot. So we can strictly regulate what comes in and what does not. Now, I will mention just a little bit of more information. Alcohol, caffeine, nicotine, all these drugs come to mind. The reason that we use these drugs is because they are capable of passing the blood-brain barrier and affecting your blood's chemistry. So, for instance, if you take a cigarette, take a drag off of it, the nicotine goes into your bloodstream via your alveoli, and the nicotine will affect the nicotinic receptors in your brain within like 15 seconds. So it's an almost instantaneous augmentation of brain chemistry. There you go, man. So the reason we use these drugs is for a reason. Yeah, all right. Now, there are a few points of entry that must be guarded. All the capillaries in the brain are especially set up to have tight junctions. You guys might remember tight junctions. These are going to restrict the way in which materials can get into brain tissues. And also there are capillaries in the choroid plexus that make cerebrospinal fluid that have to be tightly guarded as well. You have neuroglial cells that are specially set up to protect these vulnerable areas so that nothing bad can get into the brain and cause damage. Because remember, if you damage a neuron in the brain, it can't heal. Okay, it doesn't grow back. Now, I will point out one more little concept. You know that your hypothalamus controls all of your basic autonomic functions. To do so, the hypothalamus has a close relationship with the blood to constantly test your blood chemistry. So the blood-brain barrier is quite permeable around the hypothalamus, so that the hypothalamus can constantly test your blood chemistry to make sure that your body is working effectively. All right, that works. Let's go here. I'm not going to go into a huge amount of detail on sleep. I'll point out a couple things. All right, first things first. You have to sleep. You have to. If you don't get enough sleep, your brain doesn't work well. You start having crazy variations of hormones in your system, and you feel depressed, and you quit thinking clearly. You can't make good decisions. You must sleep. It's just terrible, but we have artificially prevented sleep in animals before, and they lose their ever-loving minds and eventually die from it. They die from sleep deprivation. After a short period of time, you must sleep, or else you're physiologically incapable of doing what you're supposed to do on a daily basis. Now, the main bits of sleep that are important are referred to as being REM cycles. REM means rapid eye movement, and you can see on this image here, this fella, his eyes are jerking around like crazy. That's because he's going through REM sleep. You tend to enter REM sleep about every 90 minutes or 5 times in a night if you're sleeping appropriate amounts. And what we think is happening during REM sleep is you are taking your short-term memory from a structure in your brain called the hippocampus, right? Short-term memory, and putting that into long-term storage out in your cerebral cortex. So the concept is that your cortex stores long-term memory. You're doing all these things throughout the day. You're seeing new things, picking up information, and when you lay down and you go to sleep during the REM cycles, you will take that short-term information and stick it into long-term memory if it's worth knowing. You probably have met someone before and you're like, hey, I'm John. And they're like, oh, I'm Stan. Oh, nice to meet you. Then 2 minutes later, you forgot their name. That's because your hippocampus basically got rid of those nervous connections because it didn't think it was important enough to hold on to. Whereas your long-term memory, you can remember it for a duration. All right, it's a matter of getting it from the hippocampus into the cerebral cortex, and you must sleep to accomplish this. In fact, during REM sleep, if we look at electroencephalograms, during waking moments, this is how your ECG would look, and during REM sleep, it looks almost like a waking moment. In fact, we can do PET scans, and we see that the brain is more active during REM sleep than it is when you're doing algebra or something like that, or learning scientific concepts. So REM sleep is probably when we're converting short-term to long-term memory. And that would make sense too, because this is when we dream. Like our most intense dreams are during REM sleep. And Freud would say that all dreams are made up of, well, it's Freud, so it's always something about sex. But then the other 2 bits are important for us here. Something from the day and something from the past. The idea is that when we're converting short-term to long-term memory, we're relating our short-term memories to things that are already in long-term memory. So we dream about something from the past and something that happened that day. It's kind of fascinating. All right, yeah. Sleep has a restorative effect. You gotta sleep. You can't just lay down. Look at that handsome little man. Oh my gosh, he was a little baby back then. Yeah, I'm pretty happy with that. Let's leave it there. We'll move on to the degenerative brain disorders. These are Alzheimer's, Parkinson's, Huntingtons, and Lou Gehrig's disease. I'm not going to spend a lot of time on these. I just want you to get an idea so that you can kind of recognize some warning signs which may be important to you in the future. All right, Alzheimer's disease. This is a huge number of people whom are older. So if you're over 65, between 5 and 15% of folks display some degree of Alzheimer's. People over 85, about half display some degree of Alzheimer's. This tends to be just a fact of life. As you get older, your chance of experiencing Alzheimer's-like symptoms goes up dramatically. So what are these symptoms? Typically memory loss, especially short-term memory. The concept is that the hippocampus begins to degenerate and not function as well as it should. And if the hippocampus is degenerating, that means your short-term memory goes with it. You get a short attention span, kind of disoriented. If the Wernicke's or Broca's areas of your brain get damaged from Alzheimer's disease, you can lose language and generally irritability, mood changes, hallucinations, you name it. Let me tell you about my grandmother, all right? My grandmother on my mom's side, wonderful lady, but there towards the end, she had pretty significant Alzheimer's symptoms. And I don't mean to make light of this, it just is funny because she was funny, okay? She was hilarious her whole life, and that never changed. We'd go see her, and she'd be fussing at folks, be like, oh my gosh, there's they brought in an entertainer out here, and he's doing this thing for all these folks, and they're all having a great time, and I had to sit in this room. And we go and we ask, and they're like, we don't have any idea what she's talking about. She was believing that it had happened. She was hallucinating, but it never took place. Okay, never took place. She would tell us about how at night the birds that are flying around the hallway drive her crazy. I don't know how those birds get in here. There were no birds. She would at times think that For instance, my mother was still pregnant with her first child, who was my older brother, and we're all sitting in the room with her, and giving my mom the hardest time. So yes, okay, these are classic symptoms of Alzheimer's disease. I remember one time, talk about mood swings. My mother sitting in there, and my grandmother says, "Linda, why don't you sing me something? Sing me a song." So Mom starts to sing a song. She gets right in, and 5 seconds later, my grandmother looks at her and goes, "Linda, sometimes I wish you'd just learn when to shut your mouth." I was like, so funny, so funny. Like, why are you singing? Golly, it's great moment. So yeah, these are classic symptoms of Alzheimer's disease. It's just a fact of life. A lot of us are going to experience it. So just realizing that this is in the future is part of the fight. All right. What causes this? Typically a buildup of what's called beta amyloid protein. This will turn toxic and cause neural damage. In essence, the axonal tracts that kind of keep the neuron functional break down, and when they break down, you can't fix damage to the neuron or bring about augmentations therein, so the neuron tends to die. The axon breaks down and degenerates, so you end up with major damage to the brain. Reduced numbers of neurons and thus problems. You can see how small the brain is here compared to up here. Yeah. All right, now we can prescribe medication that can slow this down, but there is no fixing it. Same thing with Parkinson's disease. Earlier onset here, between 50 and 60 years old, and earlier for that matter. What will happen here is this classic pill rolling of the hands, shaking and shuffling around. This is classic Parkinson's disease characteristics. This is caused by the dopamine releasing neurons in the brain no longer functioning as well as they should, so they don't release as much dopamine, and because you're not releasing as much dopamine, the neurons there get oversensitive, and it leads to these juddery, shaky motions that we associate with Parkinson's disease. Now, we're getting pretty good at treating this these days. 2 drugs in suite in particular, called L-DOPA and deprenyl. The idea is that L-DOPA gets through the blood-brain barrier and breaks down, releasing dopamine that the brain then uses, and then deprenyl slows down the breakdown rate of dopamine so it stays in situ longer. And using these 2 drugs together, we can really hamper the effects of Parkinson's disease. So you can go and look at Michael J. Fox. He has had Parkinson's for a long time, and he's still relatively stable. He can still act from time to time. I watched him playing a guitar on stage not terribly long ago. The idea is that these drugs can slow the effects down, but they can't stop it. Okay, you can't stop it. Huntington's disease, caused by a mutant protein called Huntington that builds up and starts to kill off brain cells. This is the brain of someone in late stage Huntington's disease. The sad thing here is this begins early on, kind of middle age, and you tend not to live terribly long after you're diagnosed with Huntington's disease. Now, one of the problems here is excessive dopamine. We can use dopamine blockers to slow the progression of this down, but there is no fixing it. All right, no fixing it. Again, Huntington's disease kind of associated with these jerky motions. They refer to as flapping motions, which I will not demonstrate, but in general mental breakdown, right? The brain starts to die off, and as the brain dies off, the person is no longer the person they were before. Terrible, terrible. All right, Lou Gehrig's disease, or amyotrophic lateral sclerosis. So Lou Gehrig's disease is terrible because it affects motor neurons. Everything else is completely intact. This is Stephen Hawking. He is deceased now, but he is quite famously the face, if you will, of Lou Gehrig's disease, other than Lou Gehrig, I suppose. What happens here is motor neurons within the brain break down, and as these motor neurons break down, you can't respond to stimulation. So your sensory neurons are completely intact. Your interneurons of your brain completely intact. You know everything that's happening, but you can't respond. Once you get to a stage like Stephen Hawking here, he is mentally completely aware of the world around him, but he can do nothing more than moving his eyes. He can't really move in any other facet. Absolutely terrible. So you know everything that's happening, except you can't provide any motor outputs. Yeah. All right, that's good enough. Let's keep it on rolling. All right, and then we have strokes. So a stroke can be brought on by a whole host of things, but this tends to be males, older males, especially if you live an unhealthy lifestyle. You can certainly be predisposed towards stroke. And males tend to also have a further problem with stroke because males display a high degree of what's called cerebral lateralization. So one side of the brain kind of runs the show more so than the other. So if you get a stroke and it damages that side of the brain, it tends to just be catastrophic. Okay, catastrophic. What happens with a stroke? These can come in two forms. Ischemic strokes. This is where you get a blood clot and part of the brain goes anoxic and thus not enough oxygen, the brain doesn't function, versus a hemorrhagic stroke. A hemorrhagic stroke is where a blood vessel bursts and as such the brain is not getting appropriate levels of oxygen. Now, let's just talk about it. What you need to realize here is that a stroke is a matter of time, all right? If you see somebody and part of their face begins to droop, they can't lift an arm, you know, they're generally lethargic. You try to talk to them and they're having trouble understanding you, or they try to talk back to you and they're making no sense. One side of the body seems not to be working the way it's supposed to work. These are classic examples of a stroke taking place. When you see this, you go to the emergency room immediately. Because if you get there fast, solid chance you can take care of the problem and the person will be all right. But if you wait, you get nerve damage and there's no coming back from it. All right? No coming back from it. I hear stories all the time from people that were having a stroke or stroke-like symptoms, go to the doctor, they administer an anticoagulant if they're having an ischemic stroke, and they're just fine. Totally okay. It's like, man, I don't know what's going on. I'm okay though. And then there's a situation like my father-in-law's dad, okay? My wife's grandfather. He started having stroke-like symptoms, and he's a big hard-headed guy, so he refused to go to the doctor, and they had to drag him out to the car, throw him in, and he still wouldn't allow him to do anything. They had to call paramedics. Paramedics finally came and got him. Hours had gone by. He never walked again. He was never fully cognizant of the world around him again. He died shortly thereafter because he was not there. The guy that was there before was gone, all right? Because he delayed it and ended up with major brain damage, all right? You think you're having a stroke or you see somebody that may be having stroke-like symptoms, you get them to the doctor immediately, and there's a solid chance that they'll be all right. We use this FAST technique to diagnose stroke victims. Face, you can see one side of the face drooping or not functioning correctly. That's a good example of a stroke. Arms, tell the person to raise their arms up. If one arm doesn't really work the way it's supposed to, it's a good example of a stroke. Speech, if you can't understand them, they can't understand you. Good examples of somebody potentially having a stroke. And then last but not least, time. Get them to the doctor immediately if you want to decrease the risk, all right? Cerebral lateralization, just a few more little topics to cover here. Lateralization is kind of fascinating. I mentioned this a few minutes ago, but the concept is that most people have their brain sort of run by one side, all right? We tend to have one side of the brain sort of running things at any given period of time. This is going to be broken down as follows. There is a left hemisphere, okay, left hemisphere of the brain, which tends to be very categorical. People whom are left hemisphere dominant tend to be quite mathematical in the way that they approach things. You can break things down and see their constituent parts, very analytical reasoning. When you're balancing your checkbook, you know, you're running your left hemisphere. I like to think of this as being PC people. So this is the control room of the Large Hadron Collider, and if you look, they're all running PCs, okay? This is this categorical hemisphere. The left hemisphere is dominant in almost everyone, all right? The left hemisphere is dominant. In some individuals, however, you can have right hemisphere dominance. Right hemisphere is more of a representational concept hemisphere. Think about being generally artsy. So imagination and insight, musical and artistic skill, these are right hemisphere concepts. I like to think of this as being a Mac person. You go to Starbucks and you see somebody sitting there with like a old school typewriter working on it, and they're wearing their beret, and they've got, you know, an ascot on or something. Yeah. This is Mac people. These are right hemisphere dominant individuals. Musical geniuses would be right hemisphere dominant, whereas mathematical geniuses would be left hemisphere dominant. All right. Again, as I said, males tend to display hemispherical dominance more so than do females. Females tend to be a little bit more balanced. And again, this is a problem and probably leads to the reason that males tend to have more problems with stroke compared to females. All right. And what you see here is some breakdown of what is done on what side of the hemisphere. I would never test you on this, but I think it's fascinating, so I'd love for you to look at it. And I want to talk about how handedness plays a role in all that we're discussing here. Is this the last slide? I can't remember. Oh, we got one more. All right, let's talk about handedness. So most people on this planet are right-handed. You know, talk about all your buddies. If we had a class of 28 people here, I'd say who's right-handed, and almost everybody would raise their hand because we're in a science classroom. That's because people whom are right-handed, the left mathematical categorical hemisphere tends to be dominant about 96% of the time. So if you're right-handed, the chance of you being left hemisphere dominant is really elevated. Okay? If you are right-handed, you tend to be quite categorical, analytical type of individual. Now, there is a small chance that you could be right hemisphere dominant, but it's limited, very limited, 4%. Left-handed people, however, this gets fascinating. In the left hemisphere, about 70% of people are going to be left hemisphere dominant. Only 70%. That means there's a much higher number, okay, much higher number of individuals who could be right hemisphere dominant. So if you're left-handed, you have an elevated chance of being right hemisphere dominant. And I realize how weird this sounds. So if you're left-handed, you could potentially be more likely to be right hemisphere dominant. That's because I think it's at the pons, all information from the body crosses over. So all information from the left side of the body goes to the right hemisphere, and all information from the right side of the body goes to the left hemisphere. So if you're right hemisphere dominant, you would expect your left hand to be the one that you use more so, right? So that's the way this works. And then, of course, this could be all screwed up, or maybe that's not what that says. There is a sizable number of individuals whom are not dominant in either hand. Okay, so both hands are kind of independent. I fall into this group, and it ends up causing problems. Okay, people whom are dyslexic, for example, like I am, man, let me tell you, I struggle with putting letters where they go in sentences and putting words where they fit together. Like I mix things up all the time. Like I can read that and I get it completely. I don't even notice that it's messed up. But the only positive aspect, I can play a guitar and a trumpet. So, you know, both, there are benefits, I suppose, but I would much rather be able to write a sentence coherently by comparison. So yeah, indeed. So that is cerebral lateralization. We'll talk a little bit about neural processing, and then we will call it a day. So in the realm of neural processing, there is serial processing and parallel processing. So when we think about things, sometimes that information is processed in a serial fashion. That is where one thing leads to the next thing, leads to the next thing, quite predictably in everyone that have experienced that stimulation. So in other words, if you touch something hot, you pull your hand away immediately, that is serial processing. Every human being that touches that hot thing will pull their hand back because it's like a reflex arc. All right, serial processing is an all or nothing response, that's a fact. Very predictable, everybody has the same reflex. That is serial processing. Parallel processing is a lot more complicated than this. You can have a single stimulus give you multiple different unique pathways. Everybody sees it differently. We all have different responses to the same stimulation. For instance, here we have a nice big McDonald's hamburger. When I see this, I think about going to school and coming home with my brother. We would occasionally drive through and pick up McDonald's, and it was delicious. Back in our high school, his high school, my junior high days, I think about riding around in his 1984 Toyota Supra, which was a complete piece of garbage and smoked like terribly. We'd have to put oil in it every time you filled it with gas. That's what I think about when I think about that McDonald's hamburger. Like I see it and it reminds me of a different whole situation. When you see that McDonald's hamburger, you think about something completely different. That's parallel processing. You've probably heard the phrase, seeing the forest, not just the trees. Parallel processing is seeing the forest. All right? Seeing the forest. And, all right, quick point. So this is Las Meninas by Diego Velázquez. When you see this, there's a lot happening. And what you notice and what you get from a great work of art of this fashion, that's parallel processing. All right? That's parallel processing. All right. I tell you what, team, I'm pretty happy with that. Go ahead and you can read through this. I think it's fascinating, but I'm not going to go into detail on it. I'm not going to be testing you. And I know this is probably getting pretty long, so I want to keep it concise. So, have a good day. I will put up a quiz on this shortly. And thank you very much. Enjoy.